So, on behalf of IGNOU Regional Center Bhubaneswar, I welcome you all to this online platform, which is uh, based on the conduction of your theory classes. And from the last few days, we have already taken 3 classes on your course code MCH-20, which is based on atomic and molecular spectroscopy of your program MSc CHEM, MSc Chemistry. And in our last 3 classes, we have completed 4 to 5 units of your MCS20 paper. And today we will have the last class, and the rest part of your course code will be completed by today. So as I experienced that only Surupananda was joined to this class. So Swarupananda, where are you from, and from which college you have done your degree, that is BSc degree in which subject?
Good evening,
Swarupananda.
sir. Sir,
Good
pranam.
evening. Hmm.
I am from Buguda and People's College Buguda, my degree.
Buguda means which district?
Ganjam.
Ganjam, right. So in your BSc degree, what is your honors subject?
Chemistry honor, sir.
Chemistry. Okay. So what are you doing now?
Sir, preparing for RHT and JT.
Junior teacher.
Or RHT, high school teacher.
Acha, high school teacher. Okay. So you have completed your BA BEd program.
Yes, sir.
Okay. So why you opt for this course, MSc Chemistry?
Sir, PGT ପକେଇ ପାରିବି ବୋଲି ଇଚ୍ଛା ଥିଲା ମୋର MSc କମ୍ପ୍ଲିଟ୍ କରିବା ପାଇଁ PhD ବି କରିବା ପାଇଁ ଇଚ୍ଛା ଅଛି.
Okay. All the best. Okay. Thank you.
Thank you, sir.
So Pramodini also joined. So uh, okay. So in our last 3 classes, we have discussed the fundamentals of spectroscopy, that is based on your different parameters of wave, and that is wave number, amplitude, wave length, frequency, velocity, and energy. Then followed by the electromagnetic radiation, which are the rays which are associated with both electric and magnetic field, and known as electromagnetic radiation. And they have the velocity that is equals to velocity of light, and they can travel to vacuum, and they do not need or require any type of medium for their propagation. They can even travel through vacuum. So these are basic properties of your electromagnetic radiation. And then we will have the that is Beers-Lambert's law, that is your observance and transmittance, and followed by your statement for your Beer's law, that is when a monochromatic light is allowed to pass through an absorbing medium, the rate of decrease of intensity of light with thickness is directly proportional to concentration of the solution as well as the path length. So this is the Beers-Lambert's law we have, and on the basis of this law, we have the equation that is A equal to epsilon BC, where A is the observance, epsilon is the molar absorptivity, B is the path length, and C is the concentration. And also we have the equation for that is your transmittance, which is but T equal to P0 by P. Okay. So this is about Beer-Stammer's law, and after that we have the mm, equation that is for your relation between observance and transmittance, that is A equal to minus log T. This is the relation between observance and transmittance. Then we have discussed the photoelectron spectroscopy, in which we have discussed the X-ray photoelectron spectroscopy, that is XPS. And as we discussed that the source of X-rays are aluminum or magnesium, alpha sources are there, aluminum and magnesium. Followed by we have the after photoelectron spectroscopy, we have your rotational spectroscopy, in which we have discussed the physical aspect of a matter and its rotational spectra, and where we have the equation that is um, E equal to bjj plus 1, where b is the rotational constant, and we have the equation that is bjj plus 1, where the selection rule is your delta j equal to plus or minus 1. Then we have the vibrational spectra in unit 4, in which we have discussed that due to presence of interparticulate space, we may say it as the intermolecular space or interatomic space, otherwise known as the voids. These rotational as well as vibrational motion can be possible among the gaseous particles. And we have for your vibrational spectra, we have the equations, and we see that your delta V in your vibrational spectra, your selection rule is delta V equal to 0. It is not allowed transition, but delta V equal to plus or minus 1, it is allowed transition. As your vibrational labels of a substance, it is associated with many rotational labels. So for your vibrational and rotational spectra of a molecule, we have a series of bands which is uh, known as your overtones, and P series, Q series, R series, and S series. So under P series we have delta V equal to plus or minus 1, and under R we will have the that is from 0 to 1 it is P series, from 1 to 2 it is R series. And just see, I sharing my screen with you. So this is the unit we have, that is rotational and vibrational spectroscopy of a molecule. Just see this diagram. So from uh, when your del j it is plus or minus 1, this is your allowed transition. And so here we can see that we have two vibrational labels, that is del v equal to 0 and v equal to 1. This is written at the right hand side of the diagram. And just see each vibrational label, it is associated with a number of rotational labels, that is v equal to 0, this involves j double dash equal to 0 1 2 3 4 5 6. Similarly for v equal to 1, we have many rotational labels, that is your J dash equal to 0, 1, 2, 3, 4, 5, 6. And when the transition is occurred between del V equal to plus or minus 1 and del J equal to plus or minus 1, then we will have allowed transition. So just see here, when for V equal to 0, when the J double dash it is equal to 1 and the transition is from J double dash equal to 1 to J dash equal to 0, that means from 1 to 0, that means it is minus 1 transition, del J equal to minus 1, because it is final state minus initial state. So this is 0 minus 1, it is equal to minus 1. So this is the allowed transition, and this is also del V equal to plus 1, because this is a transition from V equal to 0 to V equal to 1. So that means this is an allowed transition. And similarly, in the transition from J double dash 2 to J dash 1, it is also allowed. So J double dash 3 to J dash 2, J double dash 4 to J dash 3, J double dash 5 to J dash 4, and J double dash 6 to J dash 5. So all the blue lines, these are all involved your del J equal to minus 1 and del V equal to plus 1. This is allowed transition, and this series of lines known as the P series. And similarly, when del J equal to plus 1, that means it is from J double dash equal to 0 to J dash equal to 1. So J double dash 1 to J dash 2, J double dash 2 to J dash 3, J double dash 4 to J dash 5, J double dash 5 to J dash 6. So all the red lines, these involves del J equal to plus 1 and del V equal to 0 to plus 1. That means these are also allowed transitions, and here your del J is plus 1. So these are all your allowed transitions, and you just see the blue lines of the transition are known as P series, and the R lines, these are known as the R series. And in all these transitions, the energy gap between two successive P series or R series, it is uh, determined as 2B. Okay, and the energy gap between P1 to R naught, it is equal to 4P. This is already calculated, and all these equations are discussed yesterday. So like this, we will have different series, that is P, R, then for S and Q we'll have the plus 2 and minus 2 transition. So all these you just see, and we will have different series. Here it is written the P branch series and again the R branch series. So how your energy is calculated and everything, it is already given here. Then today we will have the discussion, that is the discussion for your vibrational spectra of polyatomic molecules, and this is your last unit of your MCH-20. Okay, and your vibrational spectra, it is also known as the microwave spectra or your IR spectra, we may say, because your IR spectra, when IR radiation, it is if some it has some interaction with the matter, then that spectroscopy is known as vibrational spectroscopy, IR spectroscopy, in which the organic component, the functional group gets vibrated, and we have different data collected from for your IR series. So your one important application of the spectroscopy is for the identification of unknown compound for an organic compound. Certain bonds in organic molecules are associated with characteristics IR band in specific spectral regions. For example, when alkane is there, your IR absorption frequency, it is 2800 to 3000 centimeter inverse. When alkene is there, when aromatic CH it is connected, then your region is between 3000 to 3200. Similarly, we have the alcohol with non-hydrogen bond and hydrogen bond. For non-hydrogen, it is 3500 to 3700 sharp, and for hydrogen bonded, it is 3200 to 3500 broadband. So this is one example of IR spectra for your ethanol component, which is given here, and we will have the hydrogen bonded at around your more than 3000 and less than 4000, but when CH stretching between frequency, it is occurred at nearly 3000. So alkynyl alkyne carbon carbon bond, the stretching frequency also can be calculated. For example, when we have the double bonded carbon, it is having 1640 to 1675, and for triple bond it is 1950 to 2300 centimeter inverse, because when triple bond is there, your force constant is more. When force constant is more, your frequency will be more. So that's why the triple bond absorb at higher frequency of higher radiation than the double bond. This is the example we have, that is the cis 3 hexene, when we have the stretching frequency of alkene at around 3000, and when the transform is there, we have the different stretching frequency. Okay, and here CC double bond C stretch is missing, and this is not needed for your physical aspect. And the region from 900 to 1300 is called fingerprint region of the spectra. So in this region, we typically find many peaks arising from various low energy species and bending motion of the molecule. So before, as we know that in every spectra there is an unique region which doesn't coincide with the other region of the spectra, and which is known as a fingerprint. As the one fingerprint of a human doesn't match with the other human being. Uh, so like this, the fingerprint region of a molecule, of one molecule, it is doesn't coincide with the fingerprint region of the other molecule, and this fingerprint region, uh, it is lies between 900 to 1300 centimeter inverse. So in this region, we typically find many peaks arising from various low energy stretching and bending motion of the molecule. So as we already discussed, that we have symmetrical stretching, asymmetric stretching. Under bending, we have scissoring, wagging, rocking. All these forms of bending vibrations are possible. So for your fingerprint region, we have very low energy stretching as well as bending. Frequency of absorption is possible. So it is very difficult to assign peaks in this region, because, but they are very different even for closely related compounds. So this is used for confirmation that a particular compound has been isolated. So this fingerprint region, it is mainly useful for the separation of a compound from a mixture. So fingerprint region of cis and trans 3 hexene as compared here, that for your cis one, your fingerprint region is around your how much 1100 something, but for your transform, it is around 1000 plus centimeter inverse. So this is how the fingerprint region, it is characterize the difference between cis and transform of 3 hexene. Molecular dipole moment. So as we know that when a molecule is having the dipole moment, that is it has two polar poles, or it is treated as a dipole, then it is IR active. So for a vibrational spectra, the molecules should have the IR active nature. For example, your carbon dioxide, which is a linear shape molecule, And here we have two type of stretching frequency. One is symmetric and another is asymmetric. With the symmetric one, so in symmetric carbon dioxide, the stretching frequency is zero and it is inactive, because in symmetrical we have the dipole moment of zero. But in asymmetric stretching, we have the higher active character, because some dipole character is developed in your IR, that is your asymmetric stretching mode. So a bond dipole is a slight separation of charge between two non-identical atoms connected by a bond. The size of the bond dipole is proportional to the amount of charge separation and to the bond length. So this is very clear that when the charge separation is there, uh, as well as the bond length plays an important role for your higher active characteristics. The dipole moment of a molecule is the vector sum of the bond dipole. So a polar molecule has a non-zero dipole moment when it is stretched or bent symmetrically. Then, except in diatomic, molecular vibration generally involve motion of several atoms. More than one bond is deformed at a time. So this is very obvious that irrespective of the type of constituent atoms present in the molecule, your dipole or your polarity involves motion of the several atoms in different directions. So the vibrational mode must conserve overall molecular momentum. So when we predict the dipolar character of the molecule, we should determine the overall molecular momentum in different directions. We can choose vibrational mode that are independent motion called normal modes. So we have different type of normal modes in a molecule. So a molecule made up of n atoms will have three n different ways. Now, one direction of motion per atom per Cartesian axis. As we know, we um, we analyzed the molecule or the constituent atom of the molecule in three different axes in three-dimensional space. So that's why we have a 3n degrees of freedom for every atom in a molecule. And we have three types of motion primarily, that is translational, rotational, and vibrational degrees of freedom or motion. The translational motion it is 3, the rotational motion it is 3, and the vibrational motion for non-linear molecule it is 3. So the vibrational motion or vibrational degrees of freedom for your non-linear molecule, it will be 3n minus 6. 3n is the total degrees of freedom, and 6 is the 3 for your translational, 3 for your rotational. So 3n minus 6. But for a linear molecule, 1 degrees of freedom or 1 degrees of freedom for your vibrational motion, the vibrational degrees of freedom, it is cancelled in the internuclear axis, as a molecule is linear. So that's why one vibration will be merged. And then we have the formula that is 3n minus 5. So you just when you face any question related to the determination of vibrational degrees of freedom for a particular molecule, then you just first predict whether the molecule is linear or non-linear. If it is linear, you have the formula 3n minus 5, because one vibrational degree of freedom, it is cancelled or it is merged in the internuclear axis or the axis of linearity. Then for a non-linear molecule, your formula will be 3n minus 6. Just see here. Here it is given for your water molecule. We have three atoms. That means the total degree of freedom will be 3 into 3, that is equal to 9. So as water is a non-linear molecule, so here we have the uh, vibrational degree of freedom will be 3n minus 6. So that is 3 into 3 minus 6. It will be 3. So what are the three? One is stretching, what is asymmetric stretching, and one will be bending. So these will have the three type of vibrational degrees of freedom of vibrational motion which are possible in water molecule. Then we have the carbon dioxide. So carbon dioxide is a linear molecule. So the formula applies here is 3n minus 5. So this is 3 into 3 minus 5, which is equal to 4. That means here we have the 4 degrees of freedom which are vibrational degrees of freedom. So one will be symmetric stretching where the two oxygen atoms are stretched in the opposite direction, and one is asymmetric stretching in same direction, and two will be bending, that is symmetric bending and asymmetric bending. Then we have the selection rule. So a selection rule is the rule that tells us when a particular kind of spectroscopy event can occur or not. So the selection rule helps us to predict which transition is allowed and which transition is forbidden. So for example, when your vibrational spectra, when delta V equal to 0, it is forbidden. But when delta V equal to plus or minus 1, it will be allowed. So in IR spectrum, the key selection rule is that the dipole moment of the molecule has to change during the vibration. This is very important. So for a molecule to be IR active, the change in dipole moment should be positive, and so we can have that IR spectra. So a normal mode that can absorb an IR photon is said to be IR active. For example, this one. Now, which one of the mode is IR active? Just see here. In symmetric stretching, your dipole moment is 0. This is IR inactive. So for the asymmetric stretching, the dipole moment is positive, or this is non-zero. So that's why asymmetric stretching is IR active. Similarly, for bending vibration, your dipole moment is 0 as both are in opposite direction, carbon in one direction and oxygen is another direction. Here also it will be inactive. So these are some bands which are expected in your IR spectra. Then this will be transmittance versus wave number. Okay. Then your combination band will be there. Asymmetric stretching around 2300 around. Then one bending vibration, it is around 700 centimeter inverse is there. And all the uh, uh, vibrational frequencies of the corresponding functional groups are there, and which is given in a tabular format in any theoretical book. Then a normal modes of water in air spectra. Then we have the symmetric stretching, asymmetric stretching, and bending. Just analyze the three forms of your water molecule and accordingly predict whether they are reactive or inactive. In application, one is Earth heat balance. So energy of the sun mostly arrives at the Earth in the form of visible light. Note that the atmosphere is essentially transparent at optical wavelength. The Earth reflects some energy so that but observe a lot of it. Averaged over the whole planet, about 30% of the light coming in is just reflected back to space. The planet radiates mostly in the IR region. The atmosphere contains many gases that absorb in IR. So some of the radiation from the earth, it is absorbed in the atmosphere. But then what happened to energy captured by the atmosphere? So when gaseous molecule becomes vibrationally excited, by absorbing IR radiation, the excess vibration can be converted to translational kinetic energy during collision. So energy is constantly redistributed in collision and other energy transfer processes. A gas at temperature T also emits black body radiation. So this is all the application of your IR. Then this is earth heat balance. When carbon dioxide it is bent, this emission intensity versus your wave number. Then we have a curve. The first is at a temperature around 220 Kelvin. The second green color it is around temperature 288 Kelvin, and the third that is purple it is around temperature 320 Kelvin. So then we have the application that is greenhouse gases. So for the greenhouse gases, as we know, the earth temperature it is increasing day by day due to greenhouse effect, and it is your nitrogen or oxygen or argon, the major component of the atmosphere, do not absorb in the air. The next two most common component of the atmosphere, water and carbon dioxide, do absorb in air, because nitrogen, oxygen, argon, these are all non-polar molecule, whereas your water as well as carbon dioxide it is polar molecule. And in carbon dioxide we have symmetric and asymmetric stretching and bending are there, which are IR active. So your gases that absorb in the air are called greenhouse gases. The atmospheric water content is set by the balance of evaporation and precipitation, which depends on the atmospheric temperature. It is a responding variable. We worry a lot about carbon dioxide because we are adding a lot of it to the atmosphere, which affects energy transfer through the atmosphere. Then we have the photon reabsorbed versus lost to space. So at lower altitude, photon emitted at wavelength that carbon dioxide can absorb travel only a short distance before they are in the fact absorbed by carbon dioxide molecule. Similar statement could be made about other greenhouse gases in their respective absorption ranges. So absorption of IR photons slows the migration of heat through the atmosphere. So near the top of the atmosphere, where carbon dioxide concentration is low and pressure is also low, there is a much larger probability that a photon emitted towards space will actually escape without being reabsorbed. So it is important fact that at those altitude the atmosphere is a lot cooler when your high altitude atmosphere. Then we have the carbon dioxide concentration and temperature versus altitude curve. Then it is seen that we have the carbon dioxide curve, that is its concentration is gradually decreases when your kilometer range is just increasing, and also the temperature where we have the uh, temperature that is when your kilometer increases, the temperature is also decreases. Yes. When earth emissions spectrum for your water, carbon dioxide at different temperatures, methane, ozone, then we have the atmospheric water. These are all demonstrated on one diagram or figure, that is wave number, wavelength, and radiance. We go through this. We have the interpretation of earth emission spectrum. That the emission of carbon dioxide comes from high in the atmosphere, where it is cool and there is not much carbon dioxide to block the outgoing air photon. Emission from water comes from lower down where it is not quite as cool, since condensation of water prevents it from getting too high in the atmosphere. So we have the it depends on the concentration of carbon dioxide. Then we have the interpretation of our emission spectra, that is on the surface of our Earth we have the incoming solar radiation, visible light reflected from the surface, non-greenhouse air photons, water photons get escaped, we have the carbon dioxide photon get escaped, and we have the ground greenhouse photon trapped by the surface of the Earth. Then the greenhouse gases like carbon dioxide slows the escape of heat from the atmosphere to space. A simple analogy is that the atmosphere acts as a blanket. This is not inherently a bad thing. The planet would be a lot colder if there were no greenhouse gases. This is very much correct because the average surface temperature would have been minus 18 degrees centigrade or 255 degree Kelvin, at which the life may not support. So it is a good reason for us that that greenhouse gases is like a blanket to our earth crust. Then adding greenhouse gases to the atmosphere is analogous to making the blanket denser, resulting in a high temperature under the blanket. Then we have the last slide, that is the carbon dioxide. So from 1959 to 2019, that is around 60 years, the CO2 concentration in the atmosphere measured at the Mauna Loa Observatory has risen from an annual average value of 316 ppm to 411 ppm, that is increased by 30%. So the rate of increase in the concentration of carbon dioxide rising from about 0.6 ppm yearly in the early 60s to about 2.6 ppm yearly, that is now. Warming induced by greenhouse gases emission is a self-reinforcing problem. So it increases the amount of water vapor in the atmosphere. On averaging, less of the planet is covered with ice, and melting uh, permafrost releases methane, a very powerful greenhouse gases. So there is no escaping the physics. Adding greenhouse gases to the atmosphere heats up the planet. So as you know, these are the major environmental issues nowadays, like your uh, greenhouse gases, your acid rain. So all these things are um, due to the uh, uh, non-environmental friendly work, predominantly by the human beings, and it is because of the overpopulation. It is over requirement of the food, then land for your reside. Okay. So the major problem is your population growth. So due to this, all the environmental issues, all these environmental degradations are there in current scenario, and it will increase day by day in near future. So then we have the uh, we have the PDF discussion, that is the last part, that is unit 6, this one, and this is your vibrational spectra for your polyatom. Just western. Hello. So let's have the discussion that is vibrational spectroscopy polyatomic molecule. And in this part, this is the last unit of your paper MCH-20, and this will be the vibrational spectroscopy. And we have discussed it for your diatomic molecule, that is a diatomic molecule, that is harmonic and anharmonic oscillator. In harmonic oscillator we have the equation, and that is omega exe, whereas the in your anharmonic oscillator we have the different equation, that is its square, its cube, will the different equations are there. So in this part we will have the discussion of your vibrational spectra for polyatomic molecule. As already discussed today, in the PowerPoint presentation, we have the polyatomic molecule IR spectra, which is your vibrational modes or vibrational degrees of freedoms are calculated. So we will begin this unit by delineating the difference in the vibrational of diatomic and polyatomic molecule. We will introduce the idea of normal coordinates and normal mode of vibration of the given polyatomic molecule. Thereafter, we will discuss about the selection rule and explain the origin of the IR spectra of the polyatomic molecule. And we will have different uh, discussion, that is the bands like overtones, combination band, and the Fermi resonance we will have. Then thereafter we will extend the discussion to the effect of rotation on the vibrational spectra from the previous unit and outline newer features. Then what are the outcomes of this unit? We will explain the concept of normal mode of vibration in polyatomic molecule and outline their physical significances. We will formulate expression for calculating the number of vibration bands for a polyatomic molecule. Also, we will give the prerequisites and the selection rule for vibrational transition in IR spectroscopy. We also compute the number of vibrational band for simple molecule and ascertain their IR activity, which is already discussed in a PowerPoint presentation. Let's have the discussion once again. Then we will define and explain the origin of hot bands and Fermi resonance, which is about your fingerprint region. Then explain the difference in the parallel and perpendicular mode with suitable example, that is IR active or IR inactive. Then give characteristic difference in the spectral band for parallel and perpendicular modes. And lastly, we have to analyze the influence of molecular rotation on vibrational spectra with emphasis on the linear molecule. So for linear molecule, we have um, active vibrational spectra as well as non-active vibrational spectra. Depends on the polarity or the dipole moment. So for stretching frequency or stretching stretching uh, symmetric stretching, we have different type of vibrational mode of vibration than the your asymmetric. Then we have the polyatomic molecule with several bonds with spectrum. It is expected to be quite complex, as each of the bonds will have its own characteristic signal. In addition to these, there is a possibility of interaction between size is quite complex. It is almost impossible to interpret all the signal obtained. However, with a little understanding of the possible vibration modes, their IR activity, we can analyze, and we can also use the spectrum to get your structural information. With just one bond, it is easy in case of diatomic molecule to visualize the vibration. As this is a polyatomic molecule, so we may analyze or we may interpret the different peaks that is obtained from the IR or vibrational spectra, and on the basis of the type of stretching and bending mode, we will interpret that which peak belongs to which uh, which type of vibration. Okay, so however, in polyatomic molecule, it is quite complex to visualize and describe molecular vibration, and also we will need to know that what is the number of independent modes of vibration for a polyatomic molecule. Now here we will have the three concept, that is spatial degree of freedom, which is already discussed. That is, we have the rotational degree of freedom, vibrational as well as the translational, and always the vibrational degree of freedom for a non-linear molecule it is 10 minus 6, and for a linear molecule it is 10 minus 5. Then the normal coordinates, that is along x, y, z, and normal mode of vibration, that is it may be your overtone, it may be your some other transition, normal transitions, and this also quite handy. So the different type of motion in polyatomic molecule. So here it is given that a spatial degree of freedom refers to an independent axis of motion of a particle. For example, when a single atom possesses spatial degree of freedom along three axes, that is x, y, z, so we have 3 degrees of freedom, that is equal to 3n, because uh, for one atom we will determine the degrees of freedom along three axes in three-dimensional space, which is along x, y, and z axis. So the total degrees of freedom it is always equal to 3n, where capital N belongs to number of atoms. So here we may we may assign the three translational degrees of freedom in three-dimensional space for your different atoms present in the molecule. So we have the three translational motions as well as three rotational motions are there. Here it is written, that is when your translational motions are when your translational motions are deducted from your total degrees of freedom, then your equation left, that is 3n minus 3. Similarly, when your rotational motion is placed, so for a non-linear molecule, your rotational motion will be 3 and your formula becomes 3n minus 6. But for a linear molecule, one rotational motion merged it is merged with the axis of linearity. So that's why we have the equation for a linear molecule. The rotational motion is 2. So your number of vibrational motions will be 3n minus 5. So for a molecule like carbon dioxide or hydrogen cyanide, HCN, where we have the uh, formula for your vibrational degrees of freedom, it is 3n minus 5, where one rotational motion it is merged with the axis of linearity. So we have the equation 3n minus 5. So for carbon dioxide, it becomes 4, and also for HCN, it becomes 4. But when non-linear molecule like sulfur dioxide, SO2, it is also a triatomic molecule. Here the total degree of freedom it is equal to 3 into 3 equal to 9. But here your vibrational degrees of freedom will be 3n minus 6. It will be 9 minus 6 equal to 3. So for your non-linear molecule, your rotational degree of freedom is 3, and for a linear molecule, your rotational degree of freedom is 2. As one rotational degree of freedom, it is merged with the axis of linearity. Then we have the normal mode of vibration. So, and here we have some quantum mechanical aspect of your vibration. That is the in normal coordinates, a linear combination of Cartesian displacement coordinates with each term weight by a constant that may be real or imaginary. Let's a vector r with the coordinates 1, 2, 3, and it is expressed in a linear sum of unit vectors, that is r equal to 1I plus 2j plus 3k along 3 axes. So when all the atom in the molecule are positioned where no net force act on them, they are said to be at equilibrium. We call their coordinates as equilibrium coordinates and define a new set of coordinates and Cartesian displacement coordinates. So here we will have the quantum mechanical aspect of your vibrational spectra. So here your Qi, it is expressed as XH minus XH minus Q2 Y, then Q3 is Z, and this is discussed for your hydrochloric acid molecule HCl. Similarly, for your chloride, we will have Q4, Q5, and Q6 along three axes X, Y, Z. So for HCl, we have six Qs, Q1 to Q6. So we will have, just wait, we will have for Q1, just see here, for Q1, it is your Q1 plus Q4, that is written as translational Tx. For Q2 and Q5, it is along Ty, that is a translation, and Q3 and Q6, it becomes your translation along Z axis. You see here, this is the table we have, that is Q1 along X, Q2 along Y, and Q3 along Z. So when translation occur, that translation means what? From one place to another, the molecule is translated or it is displaced. So for your uh, x-axis, that is Tx, the coordinates will be Q1 plus Q4, and for y-axis it is Q2 Q5, and for z-axis is Q3 Q6. This is already given here. So and the axis direction also mentioned here, that is red marked arrows. These are the primary axis for the translation along a particular direction, that is x, y, and z. So the x-axis is just horizontal, and y-axis it is vertical, and z-axis it is there. Then we have the rotation, that is rx, rq, and rz. At HCl, it is a linear molecule, so it is given here, that is Ry. We have Q2 plus Q5, and Rz, it is Q3 plus Q6, but R1 or Rx, which is coincide or merge with the axis of linearity. So we have the Q1 plus Q4, which is not be there in our final calculation. So your R becomes 2, that is Ry and Rz. Rx becomes your rotational vibration, rotational motion, but it is merged with the axis of linearity. So now here it is written, here n equal to 2, it is not 3, here it is written it is equal to 2. That means the formula becomes, sorry, the formula becomes 3n minus 5. Okay, then the selection rule. Then we already see that for a polyatomic molecule, when the molecule is linear or non-linear, harmonic or anharmonic oscillator, we have the formula 3n minus 6 and 3n minus 5. Then for your vibrational spectra, we will have the selection rule, that is delta V equal to plus or minus 1. And when delta V equal to 0, this transition will be forbidden transition or not allowed. We expect therefore absorption of radiation corresponding to transition from V0 to V1. It is allowed transition, and it is has some energy level schemes. The energy level diagram and the associated normal modes of water are given in 6.3. And you note that, chalo. we will have different energy gaps. That is, for a water molecule we have 3756 centimeter inverse of absorption, then 3652 centimeter inverse and 1545 centimeter inverse for water molecule. As water is a non-linear molecule, then the formula 3n minus 6 is applied, and accordingly the normal mode of vibrations are calculated. So each normal mode acts as a simple harmonic oscillator. Normal modes are independent, they do not interact. A normal mode represents a concerted motion of many atoms. All atoms of the molecule pass through their equilibrium position at the same time. The center of mass doesn't move during the vibration. This is very important, that the center of mass don't change its position during the vibration. Okay. Then we have the same thing, that is asymmetric stretching, that is stretching at one direction. Then we have the symmetric stretching at opposite direction, that is anti-direction 180 degree, where your dipole moment becomes zero, and at this molecule, this at this stage the IR it is inactive. Then we have the bending. Then we have the bending on the plane and out of the plane. Then the same thing for your AB2 molecule, how your IR activity, IR inactive, then your dipole moment plays an important role for your IR activity or vibration activity. Then we have the overtones, combination and hot bands. So on the basis of the different type of transitions possible for a uh, polyatomic molecule under vibration spectroscopy, we have overtones, combination and hot bands. Just see the example of hexane, that is C6H12. So it has 18 atoms. So the fundamental vibrational mode will be 3 into 18 minus 6, as this is a nonlinear molecule. So your 48. So 48 vibrational degrees of freedom will be there in your N hexane molecule. So what is overtone? So for a diatomic molecule, when for a harmonic approximation, when delta V equal to plus or minus 1, the type of transition we have got will have uh, treated as your overtones. And these allow transitions involving more than one quanta, giving rise to the first and second overtone with successively decreasing intensity. These transitions originated from the ground vibrational state, that is V equal to 0. Since at ambient temperature this is the most populated state. Then we have the Morse type anharmonic potential. Then we have the combination band. So when del V equal to plus or minus 1, we will get the overtone, and these are the allowed transitions. Then we have the combination band. This combination band includes your weak band as well as strong bands, and in addition to overtones, we have some weak bands which are obtained in vibrational spectroscopy for a polyatomic molecule, and these due to combination of these two fundamental vibration, we will get the combination band, or a difference of two fundamental called difference bands. And the frequency of a sum band is slightly less than the sum of the frequencies of the fundamentals due to the anharmonic nature of the vibration. Also, the sum bands are more commonly observed than difference band in vibrational spectra. The intensities of the overtones bands are typically 1 to 5% of that of the fundamental band. We just go through this, and these are. It is interesting to note that we may observe combination band for the fundamental vibration that themselves are not IR active. This is very important, that we observe the combination band from the fundamental band which are not IR active. The combination bands involve the excitation of two or more normal modes, that is, two or more vibrational modes are excited by the same photon, that is, these involve changes in vibrational quantum number for more than one normal modes. Theoretically, these transitions are forbidden according to the harmonic oscillator selection rule, and these combination bands, that is a combination of overtone and weak bands of the vibrational spectra, and for example, we will have carbon dioxide. The fundamental band is coming at 1330 centimeter inverse. The first overturn at 1334 of a bending vibration. We will also have a frequency of absorption at 667 centimeter inverse. These are said to be accidentally degenerate, and the energy arises above the ground state. It becomes likely two or more vibration will share similar frequencies. So then we have the Fermi resonance. So it can be shown by quantum mechanically that two such bands may interfere with each other in such a way that one at higher frequency is observed at still higher frequency, and one at lower frequency observed at a lower frequency moves towards a lower frequency. For example, two bands of carbon dioxide which is at 1285 and the other at 1385, it is around 1330 centimeter inverse. These bands are due to resonance between expected symmetric stretching vibration and a very weak overtone, and such resonance is known as Fermi resonance. So in Fermi resonance, what happened? We will have two types of bands which are obtained from a IR spectroscopy, and here your due to resonance factor, we will have two two vibrational frequencies that are due to that resonance, which is known as Fermi resonance. To observe Fermi resonance, a combination band or an overtone interact with a fundamental of same symmetry and nearly at the same frequency. The origin and location of Fermi resonance is schematically given here. Just see here. Here we will have a resonance band at red lines, that is h nu x plus x to h nu minus x, and in that above part we will have h nu dash to h nu dash, that is here the total energy it is separated with the two parts, that is h nu and h nu dash. So due to resonance we will have different mode of vibration, different vibrational stretching frequency. The difference of about 100 centimeter inverse between the bands in this carbon dioxide, it is indicated strong resonance between them. Increasingly, these signals are observed due to be of similar intensity in case of carbon dioxide. So similarly, for your aldehyde functional group, we will have a overtone for the deformation, that is the bending vibration of aldehyde group CHO group at 2800 centimeter inverse. This gives rise to Fermi resonance at 2830 and 2730. Incidentally, such a doublet in the IR spectrum of organic compound used as a kind of characteristic signal of the aldehyde functional group. So when you will have some resonance factor which give rise to different type of bands at different frequencies, then we will call it as Fermi resonance. Then for your hot bands, we will have different selection rule, and we will have the hot bands. Like for harmonic oscillator in the diagram, just see in the harmonic oscillator from V0 to V1, V2 and V3. So from 0 to 1 it is known as fundamental band. From 0 to 2 it is known as first overtone. From 0 to 3 it is known as the second overtone. But the transition from 1 to 2 it is known as hot band. Similarly, for anharmonic oscillator, just see here from 0 to 1, it is purple color fundamental band. From 0 to 2, it is first overtone blue color. From 0 to 3, it is second overtone that is blue in color. But the transition between 1 to 2, it is known as hot bands. So this is in accordance with Bose band distribution. Most of the molecule exist in their vibrational ground state. Therefore, most of the observed transition originated from this state. At room temperature, the fast excited state is too low for any transition originating from V equal to 0 level to have observable intensity. However, if we study the vibrational spectrum for the system at higher temperature, the population may become significant enough to give rise to a transition with measurable intensity. Such transition is called hot bands as these are observed at high temperature. Yes, when high temperature is implemented or it is applied within the characteristics vibrational spectroscopy, we will have a transition from level 1 to 2. It is known as hot bands. Therefore, we say that hot bands refers to transition from an already existed vibrational state. It is obvious that besides being observed at higher temperature, their intensity is also temperature dependent. Higher signal intensity at higher temperature. A schematic representation of the fundamental and hot bands are given for both harmonic and anharmonic oscillator. And these are in accordance with harmonic oscillator approximation. So just see here. So this is the thing that at a high temperature, we will have different. We will have the transition from level 1 to 2 are known as hot bands. Then the same way, if it is from 2 to 1, it is hot band, and accordingly for anharmonic oscillator, we have the delta E calculation, and after that we will have the result that is omega E, that is 1 to 4 x E. It is the energy of a hot band, and accordingly just go through this. Then we have the reasons for decrease in the number of band observed in the spectrum. So what are the reasons? The fundamental frequencies may fall outside the region under investigation. So when we go for the vibrational spectra of a particular molecule, uh, theoretically we have many vibrational peaks, but in actual sense we will get less than this because many fundamental vibrations uh, are uh, there which are fold outside the region of investigation. Then fundamental bands that are too weak to be observed, this will give a very small peak which cannot be interpreted. Fundamental vibration may be degenerate because when one line is overlapped with another line, then the two lines are merged and it seems as one line. So for this also, this is the degeneracy. We will get less number of peaks for your fundamental vibration. Certain fundamental vibration fail to appear in the IR because they may lack the region required change in dipole moment. So due to uh, that change in dipole moment also, we will face the problem of not having the required vibrational spectra for a molecule. Then effect of rotation on vibration. So we will have the selection rule delta V equal plus or minus 1, 2, 3. Then fundamental first overtone, second overtone will be there, and also we will have the rotation, that is del J equal to 0 or plus or minus 1. We will have the P, Q, R, S like series. Then we will have the parallel and perpendicular mode. So for linear triatomic molecule like carbon dioxide, the dipole moment originated, mm, it may changes for the stretching, that is symmetric and asymmetric transition may occur parallel to the twofold rotation axis, and for the bending vibration these are perpendicular. Uh, so on the other hand, for a bent triatomic molecule like water, the dipole moment changes for the symmetric stretching and bending, which are parallel to the twofold rotational axis, whereas the asymmetric stretching, these occur perpendicular to the axis. Just see here, these are parallel vibrations, where we have the asymmetric stretching for carbon dioxide and your bending for your carbon dioxide. Also, your symmetric stretching and your bending out of the plane and in plane. So your stretching, it is represented as parallel, but your bending, it is treated as perpendicular, because one atom is just 90-degree to the other atom. So the spectrum will also be similar in appearance to the fact that the atomic molecule, it will consist of PR branches which lies roughly equal space, that is 2b of either side, and the band center where they are not equal, not be any signal. Since for larger molecule the moment of inertia may be considerably larger and the B value be relatively smaller, the spacing between the lines of P and Q branches will be less, and consequently in some the signal in these branches may overlap to give band envelopes. The expanded view of the rotational vibrational spectrum of combination band of the linear the nitrous oxide, and the band center is at 2461 centimeter inverse. Just see that. See this one. For nitrous oxide, which is also known as the laughing gas. For laughing gas, the center band or the central band, it is lies at 2461 centimeter inverse. Then for perpendicular vibration, it is del V equal to plus or minus 1 and del J equal to 0 and plus or minus 1. Then for your J plus or minus 1, we will have the P branch as well as the R branch. Okay. And here we will have the difference in energy, that is omega naught minus 2b for your P branch, and for the R branch it is omega naught plus 2b, because it is del J equal to plus 1, and for P branch it is del J equal to minus 1. So it is omega naught minus 2b, and for your your R branch it is omega naught plus 2b. Just see here, the same diagram is here again. So we have the vibration level which are associated with many rotational levels. So V0 to V1. So when del V equal to plus or minus 1, we will have the allowed transition. Okay. So here just see del J equal to minus 1 transition, which are blue lines, del J equal to 0, which are black lines, these are Q lines, and del J equal to plus 1, which are red, these are the R lines. So we will have three series, that del J equal to minus 1, 0 and plus 1. Because for a polyatomic molecule, we will have the allowed transition of del J equal to 0 and plus or minus 1. And uh, here your, just see here, let's for your 1, 2, 3, 4, 5, 6. Yes. Let's for your P1, it is transition from 1 to, that is V equal to 0. Uh, in that we have J double dash 1 to J dash 0. For P2, it is J double dash 2 to J dash 1. For P3, it is J double dash 3 to J dash 2. That means it is del J equal to minus 1. Similarly, for del J equal to 0, that means same number, that is J double dash 0 to J dash 0, J double dash 1 to J dash 1, and so on. For plus 1, it is having the red lines. And in all these branches, we have the expression for Q branch where del J equal to 0, that is del E will have the equation of 3 by 2 omega E bar minus 9 by 4 omega E bar XC plus BJJ plus 1 minus half omega E minus 1 by 4 omega E XC plus BJ double dash plus 1. So then the equations are just simplified, and we will have the equation for the energy that is involved for each transition. So in this part, we will discuss the vibration spectra of your polyatomic molecule. In this part, we will have the P, Q, R, all these branches are here. So this is the PQR branch of hydrogen cyanide molecule, where we have the PQR structure of a new to bending vibration of a perpendicular band. So bending means perpendicular, it's overturned, it is parallel, and new 3, it is a stretching vibration, so only the PR branches. So here just see in new 2 we have 3 bands, and this is a triplet type of signal, and this is belongs to your PQR structure, whereas in 2 new 2 we have the bending, and in new 3 we have the stretching. Just see here the 6.15 figure. Here it is very that PQR band, that is a contour, it is very much clearly mentioned that it is just like a triplet. In the NMR spectrum, we will have the P band, Q band, as well as R band, where P band or P branch, it is correspond to del J equal to minus 1, and Q it is equal to 0, and for R it is equal to plus 1. That is blue, black, and red. So if the rotational structure of P and R branch is not resolved, we may observe a characteristics band contour as shown. So like the linear molecule, the IR active normal vibration of symmetric to molecule like your CH3Cl, methyl chloride, have their oscillating dipole moment either parallel or perpendicular to the unique axis of molecule. These two type of vibration have different rotation vibration selection rule, and consequently different rotation vibration band shapes are obtained. We will not discussing it any further, so let's have the discussion stop here. So this is all about your uh, vibrational spectra of polyatomic molecules. Okay, just see here, this is also a portion of the rotational spectrum of the bending mode of carbon dioxide. This is the bending mode of carbon dioxide, where a peak is at around 665 to 670 centimeter inverse of wave number, and accordingly it can be interpreted whether it is P, Q, or R branch. This is definitely the Q branch, because the left side it is the P, and middle one it is the Q, and right it is the R. Okay. So just try to understand these figures and don't confuse with the numbering of your vibration as well as rotational levels of this um, of your hydrogen cyanide molecule. Okay, so these there are some selection rules, and we have the band center of this one. For your nitrous oxide laughing gas, it is 2461. Then we have the perpendicular and parallel vibrations. Just remember that stretching frequency is always your parallel, but your bending frequency, it is related to your perpendicular vibration. And then the selection rule, this is very important. Del J equal to 0, it will means it is Q. Del J equal to minus 1, it is P. And del J equal to plus 1, it is your R. Then these are some polyatomic molecule where vibrational degrees of freedom is calculated by the using the formula 3n minus 6 and 3n minus 5. Then we have the high temperature. We have a transition from V equal to 1 to V equal to 2, which is a distinctive peak is obtained, which is known as hot band because it is obtained at higher temperature. Okay, so all these things are there. Then we will have the Fermi resonance at resonance condition. In combination band with fundamental, we have some weak bands known as combination band. Then we have some overtones, that is from 0 to 1, 0 to 2, and 0 to 3. 0 to 1 means it is first overtone, second overtone, and third overtone. So all these things are very much discussed, and let's have some discussion. Let's have some doubt clearance. So always remember, in vibrational spectra, your selection rule is del V equal to plus or minus 1. It is allowed transition, and for echo equal to 0, it is the forbidden transition. And del J, that is rotational spectra, the selection rule is either uh, 0 or plus or minus 1 for polyatomic molecule, and for diatomic molecule, it is always plus or minus 1. For polyatomic molecule, it may be 0 or plus or minus 1. For 0, it is Q lines. For minus 1, it is P lines. And for plus 1, it is R line. And accordingly, you just put the equation for your harmonic and anharmonic oscillator and calculate the energy involved in this transition. Then we have the quantum mechanical aspect. All these things are discussed. Then over to you, students. Let's have some discussion on your doubts or anything you wish to share. So now on you. So we have many students today. So thank you for joining. And now, if you have any doubt, unmute and ask your question related to this unit or any other unit which we have discussed previously. And you also ask any question related to your program, related to any issues you are facing in this IGNO course, and after that we will wind up. So let's start the discussion. The first student is Bapuji. So Bapuji, where are you from, and in which college you passed your degree, that is BSc degree? And if you have any doubt, unmute and ask the question. So next is Sucheta. The same Next is Yash.
Yeah, I can hear. I can hear.
Sucheta. Okay, very good.
Yeah,
So,
yeah, here. You are audible.
so yes, you are audible. So, if you have any doubt or anything you wish to ask, please unmute and ask your question. Okay, then next is Yash.
No doubt, sir.
Okay. So yes, where are you from?
Sir, I am from Baleshwar.
Okay, from which college you passed your BSc degree and which subject?
Sir, chemistry honors in FM University.
Okay. So what are you doing now?
Sir, I am doing, sir, BPM job, branch postmaster in post office.
Okay. So why you opt for this course in IGNO, that is MSc Chemistry?
Sir, I like the lecture post. I want to be a lecturer, sir.
Okay. So after completion of this your master degree, just tell me what
Yes,
are the
sir.
different route that you reach your destination.
Yes, sir.
So after MSc, the lecture job is directly you will get, or you will go for any higher degree for that.
Sir, I will try to be PhD.
Okay, very good, very good. So for after your MSc degree, you may opt for the NET examination, that's the National Eligibility Test,
Yes, sir.
and if
Yes,
you
sir.
pass that exam, entrance exam, you will be eligible for any assistant professor post in any government college
Yes,
or in any university. Okay.
yes, sir.
So my best uses. uh so next is
Thank you.
mm,
Thank you, sir.
okay, okay, next is Sasank Sekhar. Yes, you just mute yourself. Next is Sasank Sekhar. Please unmute and give your introduction and anything you wish to ask, mm, or anything you wish to share, Sasank. Okay, if Sasank is not here, then the last student we have, he's Dhruvo Charan, I think.
Sir, namaskar. I am from
Namaskar.
Balasar district.
Okay.
Sir, sir, actually, you have any YouTube class or not? Basically,
I do not understand your question. I
sir,
have.
in chemistry, if you
Okay.
have made a YouTube class, it is more helpful to us because we can learn other times, basically at evening times or night times, we can learn the subject. If
Okay.
YouTube link नहीं नहीं है सर क्या
Okay. YouTube link. अच्छा अच्छा. Okay.
सर सर
It's okay. YouTube. Okay. So YouTube link, it is already there from various teachers, different teachers in different state of India.
yes
So
yes sir
I do not have any YouTube channel. Okay. So you
sir, sir.
may you just go to the YouTube and search the vibrational spectroscopy or rotational spectroscopy. We'll got
Yes, yes, sir.
different YouTube videos as per your convenient time. Okay, you
Sir,
just
sir, sir. Yes,
watch and try to understand the things.
sir. Yes, sir.
Okay, okay, okay. Okay, okay. So where are you from, Dhruvo?
I am from Balasore district, sir.
So all are from Baleswar. So no district
Sir,
is there in Odisha.
From Puri.
Your or all the students from Baleswar
No,
are
sir, I'm
continuing
from,
MSc degree.
this is from Puri.
Okay, thank you, Dhruvo. Okay.
okay, okay.
So you are requested to mute. So two students left out. One is our Bapuji and another Sucheta. So
I'm
I
here.
okay. So Sucheta, where are you from?
I'm from Puri, sir.
Oh, Jai Jagannath.
Jai Jagannath.
So what is your outcome from this class, that is MCH-20? Whether you have attended all the classes, that is four classes.
Sir, I'm attending all the classes, but I think two classes I couldn't join. Probably that was the network issue. And
Okay.
rest of the classes I'm attending and I'm
Okay, oh,
enjoying.
you have attended. Okay, so from which college you have passed your degree, BSc degree?
It is Asansol Girls College.
So are you a Odia or Bengali?
Uh, Actually from West Bengal.
Yes,
Native
you're
in West Bengal, but now residing in Puri.
Puri.
Yes.
Okay, okay,
Actually, I
very
have completed my doctorate degree, but I need chemistry as MSc. That was my long-awaited wish to complete masters in chemistry. So that's what I'm doing. I have completed my PhD in uh, biochemistry, kind of means heavy metal, uh, kind of heavy metal toxicity on certain algae, marine algae.
okay, okay. So you are completed your doctoral degree in biochemistry.
Yeah, that is. So I
So
just want to,
from which university?
that is from National Institute of Ocean Technology,
Okay,
Chennai.
very yes, 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 that is in Chennai.
Hmm.
So what are you doing now in Puri?
Puri, I'm here teaching students. I have
Uh,
joined over here because from Chennai I had to come back due to some personal reasons. So actually I was there as working as a researcher. Then due to some
okay,
family issues, I
okay,
had
okay,
to come
okay.
back. So now joined as a teacher.
So teacher in which institute?
Mother's Public School.
Okay, Mother's Policy. Okay, very good. So so it is recommended from my side to go for a higher professional academic job, or you may say service, and I hope you will get. Okay, and in biochemistry in Odisha we have two or three universities where you will get uh, the service as per your qualification you have. And
So I know the name of the universities.
so biotechnology is in GM University, in Utkal University, and just regularly go through the newspaper or web browsing. Uh, weekly, if you search once, you will get a mini scope of applying for these services. Okay,
Yes, sir. Sure, sir. Actually,
so
because of Corona also affected a lot. That time, actually, I got selected as scientist D at central government job in
okay,
NIOT. Sorry,
okay,
IGMA.
okay,
But because of Corona, that time some disturbances came. That is anyway. Thank
okay,
you so much, sir. I'll definitely.
okay, okay. Okay, okay. Nice to talk to you, Suchita. Okay, thank you. So the last guy which is left is only Bapuji. So whether Bapuji is here or not?
Yes, sir. Namaskar, sir.
ନମସ୍କାର ବାପୁଜୀ ଯଦି କନଭିନିଏଣ୍ଟ ଅଛ ଓଡ଼ିଆରେ ବି କହିପାରିବ କିଛି ଅସୁବିଧା ନାହିଁ।
ଆଜ୍ଞା ସାର୍।
ହଁ ସୋ ମତେ କହିବ ଯେ ତମେ କୋଉଠୁ ତମର ରେସ୍ କୋଉଠି ଆଉ ତମେ କୋଉଠି ବିଏସସି ଡିଗ୍ରୀ ପାଇଛ କୋଉ ସବଜେକ୍ଟ ଥିଲା ମତେ କୁହ।
Sir, I am from Kendrapada, completing BSc, Utkal University, college, SSB College, Mahakalpada.
Very good. So Kendrapada is your study center, I think.
Again, sir.
So you are the only student in this group which reside very nearer to the study center.
Again, sir.
Okay. So why chemistry? So BSc ରେ chemistry ଥିଲା?
Again, sir.
Okay, so MSc କାହିଁକି କରୁଛ?
MSc higher study ଯେମିତି PhD କରିବାର ଅଛି ତ ସେଥିପାଇଁ ସାର୍ ଅଲରେଡି ମୁଁ ପ୍ରାଇଭେଟ କଲେଜରେ କେମିଷ୍ଟ୍ରି ଲେକ୍ଚରସିପ କରୁଛି ତ
Very good. ବି ବିନା MSc ଡିଗ୍ରୀରେ କେମିତି ଲେକ୍ଚରସିପ କରୁଛ?
ସାର୍ ଏଇଟା ଆମର ଡିପ୍ଲୋମା ଆଣ୍ଡ ବିଟେକ୍ କଲେଜ ତ BSc କୁ ପ୍ରିଫର କରୁଛନ୍ତି ତ ସେଥିପାଇଁ।
So are you a teaching faculty or non-teaching?
Teaching.
Okay. So MSc degree will help you in this field. Okay. Yes.
ଆଜ୍ଞା।
So my suggestion for you all, if you are wish to continue uh, mm, this area for your future perspective, then you should attempt or you should appear the NET exam of for chemical sciences. Okay, so this is conducted twice in a year by National Testing Agency, New Delhi. So it is in the month of June and December, and your application fee also it is 1000 or something like that, 1000 or 1200 rupees, and you should appear the exam and just download the question from the website and download all the online material available in the website, and in your leisure time try to read out all these materials and uh, mm, just try to appear the exam. If you appear the exam, you have the knowledge that what type of questions are coming and how far I am ready to appear for the exam, which part I left for preparation, which part I am strong and I can attend the questions, and all these things will be clear from your side whenever you attempt or appear the exam once or twice. Okay, and this exam is not like that I will appear once and I will qualify the exam. This is not like that. So maybe for one or two time you may you may not qualify the exam, but it will give you an experience of preparation uh, for a better perspective. Okay, so ସମସ୍ତେ ସେଇ ଅନୁସାରେ ଟିକେ ପ୍ରିପେୟାର କର ଆଉ ନେଟ୍ ଏକ୍ଜାମକୁ ଟାର୍ଗେଟ କର, ବିକଜ ଏକାଡେମିକ୍ସରେ ଯଦି ତମେ ରହିବା ପାଇଁ ଚାହିଁବ ଦେନ୍ ନାଓ ଆକର୍ଡିଂ ଟୁ UGC ଗାଇଡଲାଇନ୍ your NET exam or PhD degree it is now equivalent. So if you go for PhD degree it will need around 5 years of your life. If you go for a NET exam and with a proper preparation it will be um, two or three after attempting or appearing two or three times you will definitely crack the exam if you are a good student and a serious student. So ସମସ୍ତେ ନେଟ୍ ଏକ୍ଜାମକୁ ଟିକେ ପ୍ରାୟୋରିଟି ଦିଅ and ଯେତେବେଳେ ତମର when you are at the third semester of your MSc degree, that is third semester end. So when your third semester end হব তোমার MSc degree র, then you should go for that net exam um, to appear, because fourth semester ପରେ fourth semester ପୂର୍ବରୁ ତମେ ଥରେ ପରୀକ୍ଷାଟା ଦେଇ ଦେଇଥିଲେ ତମେ ସିରିୟସ୍ ହେଇଯାଇଥିବ ଦେ how far it is there to qualify the exam, how far you are prepared, you know these things or not, you are ready to face this type of question or not, all these things. And your igno material is the best material for cracking any exam in India, because igno material, it is very good, and all the informations are there in igno. And in our also in our colleges as well as in universities, in frequently we got reference from the igno material. And one or two of my colleagues are also have their degrees from the igno distance education, and they have got the government service as well as university service. So it is on you that how far you are serious, how far you are mm, uh, expending your time to the course, to the program, to your future aims, and accordingly you just prepare and make yourself serious always, that I have to appear the exam, I have to crack the exam, I will, or I should got the service or the job. Okay, so this is from my side. So uh, it is if you
Pardon,
have a,
sir?
if
Pardon?
yes, yes, yes,
Uh,
Sucheta.
may I know where have you done your PhD degree from?
I have did my PhD in Centurion University of Technology and Management in Bhubaneswar.
Okay. Okay. Your
Okay.
topic, sir?
My topic is based on the coordination chemistry,
Acha,
and
acha.
okay, so it is primarily on coordination chemistry.
Okay, great. Sir, I have another query as you were guiding everyone. By any chance, do you have somehow any contacts or someone who are related with like perfume industry based, or how good is this prospect? I mean, how prospective is this area? That preparation of perfume or forming molecules of for the perfume industry like that.
So you just take my number in your which is added in your WhatsApp group. Okay, you just
Okay,
personally contact me. We will talk. Okay.
okay.
Okay. So if um, anyone don't have any question or anything wish to share, then we may wind up the session for today's. And this is the last class, students, of your MCH-20 course code or paper for your program MSc Chemistry. So on behalf of IGNO Regional Center Bhubaneswar, I wind up the session, and I also learned and experienced a lot of things from you students, that how to be keep patience, and you all very are very energetic as well as very vigilant uh, when the session is going on and the discussion is on the way. And I hope that you will got your, or we will be you will be reach your destination with proper guidance from other teachers also. And from tomorrow onwards you will have the classes of your MCS 21 paper by Professor Dr. Purnendu Padhi from, I think no, and he's from Ravensa University, Cuttack. So hopefully you will have a good experience of online teaching. So thank you, students. We'll meet again in any other program, any other course. And till then, thank you to all.
Thank you.